Look around just about any process plant. You're likely to find boilers, furnaces, and many other types of heat exchangers. It's a diverse assortment of equipment, but all of it depends on heat transfer in one way or another. One way to define heat transfer is as thermal energy that's moving from one substance to another, or from one part of an object to another. This movement is a result of a temperature difference. We can show how temperature differences affect heat transfer with a simple demonstration. The ice cubes have a temperature of 32 degrees Fahrenheit. They're in water that's at room temperature, about 72 degrees Fahrenheit. Because of this temperature difference, heat transfer occurs. Heat naturally transfers from an area or substance of higher temperature to an area or substance of lower temperature. So heat transfers from the water to the ice. The heat from the water is absorbed by the ice, raising its temperature and causing it to melt. As heat is transferred, the water cools, so its temperature decreases. Here's another way to see what's going on. The molecules in the higher temperature water are moving relatively quickly. They have a relatively high average kinetic energy. The molecules in the lower temperature ice are moving more slowly. They have a relatively low average kinetic energy. The water molecules collide with the ice molecules. As the molecules collide, energy is transferred from the water molecules to the ice molecules. As a result, the water molecules slow down and the ice molecules speed up. This transfer of molecular energy between the water and the ice is an example of heat transfer. We can plot the temperatures of the ice and water on a temperature-time graph. We've speeded up the action to save time. As the water transfers its heat to the ice melts and the temperature of the water decreases. The rate of the temperature decrease slows down as the water temperature approaches the temperature of the ice, 32 degrees. This indicates that the rate of heat transfer is slowing down. As the ice continues to melt, the ice-water mixture approaches thermal equilibrium. Thermal equilibrium is the condition in which the temperatures of two substances are equalized. When two substances are at thermal equilibrium, no heat transfer takes place. Without a temperature difference, no heat can be transferred. A temperature difference is sometimes called the driving force of heat transfer. A greater temperature difference between substances produces a higher rate of heat transfer. A smaller temperature difference produces a lower rate of heat transfer. Different substances require different amounts of heat to change their temperature. The amount of heat that has to be added to or removed from a substance to change its temperature is called its thermal capacity, or specific heat. More precisely, specific heat is the amount of heat needed to raise the temperature of 1 pound of a substance 1 degree Fahrenheit. Amounts of heat are often expressed in British thermal units, or BTUs. 1 BTU is the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Water is given a specific heat value of 1. In other words, it takes 1 BTU to raise the temperature of 1 pound of water 1 degree Fahrenheit. Water is treated as a standard that other substances are compared to. For example, the specific heat of ice is 0.5, so it takes half as much heat to raise the temperature of ice as it does to raise the temperature of water. Air has a specific heat of 0.25, and steel has a specific heat of 0.115. Substances with lower specific heats require less heat to raise their temperature than substances with higher specific heat. The amount of heat that's transferred into or out of a plant process is affected by many factors, and we can't cover them all here. But 3 of the primary factors are the temperature change the substance undergoes, the amount of the substance, and the type of substance involved. These factors can be related in terms of a heat transfer formula. In this formula, the amount of heat transferred into or out of a substance is expressed in BTUs. The amount of heat transferred equals m, the mass or amount of substance involved, times its specific heat, which relates to the type of substance involved, times the difference between the final temperature of the substance, Tf, and the initial temperature, Ti. The difference between the final temperature and the initial temperature represents the temperature change. If the final temperature is greater than the initial temperature, heat was added to the substance. If the final temperature is less than the initial temperature, heat was removed. If any of these factors increases, the amount of heat transferred into or out of the substance also increases. In other words, if you increase mass, specific heat, or temperature change, the amount of heat transferred into or out of the substance also increases. If you decrease mass, specific heat, or temperature change, the amount of heat transferred into or out of the substance also decreases. This should give you a basic idea of how these factors affect heat transfer. In this topic, we saw how temperature differences and heat transfer are related, and we introduced the concept of specific heat. We also saw how the mass, specific heat, and temperature change of a substance are related in a heat transfer formula. Let's take a minute now to do some practice questions. Thermal equilibrium is the condition in which the temperatures of two substances are equalized. When two substances are at thermal equilibrium, no heat transfer takes place. Without a temperature difference, no heat can be transferred. Different substances require different amounts of heat to change their temperature. The amount of heat that has to be added to or removed from a substance to change its temperature is called its thermal capacity, or specific heat. In this formula, the amount of heat transferred into or out of a substance is expressed in BTUs. The amount of heat transferred equals m, the mass or amount of substance involved, times its specific heat, which relates to the type of substance involved, times the difference between the final temperature of the substance, Tf, and the initial temperature, Ti. The difference between the final temperature and the initial temperature represents the temperature change. If the final temperature is greater than the initial temperature, heat was added to the substance. If the final temperature is less than the initial temperature, heat was removed. One way that heat's transferred is by conduction. It's the primary mode of heat transfer within a solid or between solids in contact. For example, conduction is the mode of heat transfer through metal tubes in a heat exchanger. If the outside wall of a tube is heated, the heat transfers by conduction to the inside wall. The speed or rate at which heat is transferred by conduction depends on four main factors: the thickness of the material, the temperature difference across the material, the surface area over which the heat is applied, and the material's thermal conductivity. In the case of a tube, thickness refers to the distance from the outside wall to the inside wall. As the thickness increases, the rate of conduction heat transfer through the wall decreases because the distance that the heat must travel is increased. It takes longer for the heat to travel the extra distance. As thickness decreases, the rate of heat transfer increases. The heat has less distance to travel. Another factor is the temperature difference across the tube wall. For example, let's say that the outside wall temperature is 200 degrees and the inside wall temperature is 150 degrees. The temperature difference across the tube wall is 50 degrees. The greater the temperature difference, the greater the rate of conduction heat transfer. So a temperature difference of 50 degrees will produce a greater rate of heat transfer than a temperature difference of 25 degrees. The amount of surface area available for heat transfer also affects conduction. Surface area is normally expressed in square feet, and the greater the surface area, the greater the rate of conduction heat transfer. A larger surface transfers heat at a greater rate than a smaller surface. Thermal conductivity is another factor that affects conduction heat transfer. Basically, thermal conductivity is a material's ability to transfer heat. This ability varies depending on the material. For example, dense materials, like metals, are good conductors of heat. They have high thermal conductivity. Less dense materials, like styrofoam, are poor conductors. They have low thermal conductivity. Piping insulation is a good example of how thermal conductivity and material thickness affect heat transfer. Insulation reduces heat loss by reducing the rate of heat transfer to a minimum. Insulating materials have relatively low thermal conductivities. Also, the thicker the insulation around a pipe, the less heat will be transferred through the insulation. The temperature difference between the fluid inside the piping and the outside air may be several hundred degrees, but the insulation keeps the rate of heat transfer between the fluid and the air very low. Convection is the primary mode of heat transfer within or between fluids. Fluids are liquids and gases. To demonstrate convection, we'll heat a beaker of water on a hot plate and add some dye. As the water in the bottom of the beaker warms up, it rises and mixes with the cooler water. The movement of fluids is a distinctive characteristic of convection. Heat is transferred as the fluids move and mix. Convection heat transfer relates to how fluids move. Fluid movement is often divided into two categories: natural convection and forced convection. The type of convection depends on what produces the fluid movement. We've set up a loop to show the principle of natural convection. When we heat one side of the loop, the fluid in that side gets lighter, that is, less dense. The warmer and lighter fluid rises. It's replaced by cooler, denser, and therefore heavier fluid coming in behind it. The difference in density between the warmer water and the cooler water starts the flow in the loop. When more heat's added, the temperature difference between the warmest and coolest liquid increases, and the flow rate increases. If the temperature difference decreases, the flow rate decreases. The flow of liquid causes heat to be transferred by convection throughout the system. Instead of using natural convection, many systems use forced convection, which usually involves a mechanical device like a pump or a fan which circulates the fluid through the system. Convection heat transfer occurs within or between fluids. Heat transfer between fluids often occurs when they're separated by a solid boundary. This represents a solid wall with a hot fluid on one side and a cold fluid on the other. Heat transfers by convection from the hot fluid to the wall. Heat then transfers by conduction through the wall. From there, heat is transferred by convection throughout the cooler fluid. One factor affecting the rate of heat transfer is the temperature difference between the fluids. A greater temperature difference increases the rate of heat transfer. A smaller temperature difference decreases the rate of heat transfer. Heat transfer is also affected by the rates at which the fluids are flowing. For example, if the temperature difference between the two fluids remains constant, but the flow rate of one of the fluids increases, the rate of heat transfer will also increase. More fluid flows past the heat transfer surface, so there is more fluid available to deliver or receive heat. One mode of heat transfer is radiation. With radiation, heat is transferred by electromagnetic waves. All matter gives off energy in the form of electromagnetic waves. A major source of radiant energy is the sun, which transfers heat through relatively empty space. Some of the waves are absorbed by the Earth as heat that warms the Earth. We can demonstrate radiant heat transfer by placing two thermometers close together. One's in direct sunlight, the other's in the shade. Both thermometers are surrounded by the same air, but, as you'd expect, the thermometer in the sunlight reads higher than the one in the shade. That's because the thermometer in the sun is receiving radiant heat from the sun. One factor that influences radiant heating is the color of the substance that's absorbing heat. In plants, for example, most insulated piping is covered with shiny or light-colored materials. These materials reflect most of the radiant energy that contacts them, so they absorb little radiant heat. This helps retain the radiant heat inside the pipe. As a result, the amount of radiant heat lost through the piping and insulation is minimized. In this topic, we looked at the three modes of heat transfer: conduction, convection, and radiation. We discussed the underlying principles of each mode, and we saw how they're applied in plant processes. Let's take a moment now to try a few practice questions. One way that heat's transferred is by conduction. It's the primary mode of heat transfer within a solid or between solids in contact. For example, conduction is the mode of heat transfer through metal tubes in a heat exchanger. If the outside wall of a tube is heated, the heat transfers by conduction to the inside wall.